Have you ever felt like you're just drowning in information? I mean, we live in a world with these massive data sets, and trying to make sense of it all can feel totally overwhelming. Well, today we're going to talk about a pretty brilliant mathematical tool that helps us cut through all that noise to find the signals hidden inside. Okay, let's dive in.
So just imagine for a second you're trying to predict house prices. You've got data on everything, right? The size of the house, how many rooms, number of bathrooms, the local school quality, crime rate. I mean, the list just goes on. And each one of these is what we call a dimension. So with all these dimensions, how do you even start to figure out what's actually driving the price? What's the real signal and what's just noise?
And that really brings us to the big question for this whole explainer. How can we possibly take a data set with dozens or maybe even thousands of features and just boil it down to its essence without losing the stuff that actually matters? Well, the answer lies in a really elegant idea. Instead of treating every single feature equally, we're going to look for the directions in our data where things change the most. Because where there's more change, there's more information. Okay, check this out. This visual really says it all. Look at how these data points are scattered. If you were to squish them all onto the vertical y-axis, they'd be all bunched up together. Not much is really happening there. But if you squish them onto the horizontal x-axis, they're really spread out. That spread, or what we call variance, is telling us that the x direction is where all the action is. That's our signal. So this whole process actually has a name. It's called dimensionality reduction. And you can just think of it like data compression for machine learning. We're taking this huge, complex, high-resolution data set, and we're creating a smaller, much more manageable summary that still captures the most important parts of the picture. And the most famous tool for doing this is called principal component analysis, or just PCA for short. So let's walk through exactly how it works step by step. I promise it's way more intuitive than it sounds. So we start with our original data. And as you can see, it's really just a cloud of points scattered across a graph. Right now, it looks pretty messy, kind of like a random blob. Our goal is to find some kind of hidden structure inside all this chaos. Okay, the very first step is simple, but it's super important. We find the average, or the center of this data cloud, and we shift the whole thing so that the center is right at the origin, coordinate 0, 0. It's kind of like recalibrating our map so we have a nice standard starting point before we do anything else. Next up, we do something called standardization, and this is crucial. Imagine one of our features is house size, with numbers in the thousands, and the other is the number of bathrooms, with numbers like 2 or 3. Well, the huge numbers for the house size would totally dominate our analysis. So standardization just rescales everything. It puts all our features on a level playing field so that no single feature gets to unfairly call the shots just because its units are bigger. And now for the magic. The algorithm literally searches for a brand new axis, a new line, that captures the absolute maximum amount of spread in the data. It's like it rotates a ruler through that data cloud until it finds the one perfect angle where the points are most stretched out. You can see it right there, that green line. That line, that direction of maximum information, that's our first and most important principal component. So the final step is to project our data onto this new line. Just imagine that green line is a wall, and you shine a flashlight straight down from above. Every single data point would cast a shadow onto that wall. We're basically collapsing all of the information onto that one line. And just like that, we've taken a messy two-dimensional data set and reduced it to a single dimension that still holds most of the important information. Pretty cool, right? So let's just put that all together. The entire PCA algorithm really boils down to these 4 steps. First, we center the data. Second, we standardize it to level the playing field. Third, and this is the math-heavy part, the algorithm computes those new optimal axes. Now, in linear algebra, they're called eigenvectors, but don't worry about the name. Just think of them as the axes of maximum information we just found. And finally, we project our data onto those new axes. And that, in a nutshell, is PCA. Okay, so that's the how, but what about the why? I mean, why go through all this trouble? Well, the payoff comes when we apply this really elegant process to a truly massive real-world problem. Let's take a look. And this is where it gets really amazing. This is the famous MNSD dataset of handwritten digits. Each one of these little images is 28 by 28 pixels. That's 784 different features for a computer to look at. For every single image, it's basically impossible for a machine to learn from that directly. But PCA can take all 784 of those pixel dimensions and distill them down to just a handful of principal components that capture the essential 8-ness of an 8, or the 3-ness of a 3. It finds the core patterns that actually define each digit. It's also super helpful to know what PCA is and what it isn't. PCA is an absolute master at simplifying and summarizing your data, at finding those core patterns. What it doesn't do is label or categorize the data. That's a totally different job for other machine learning tools, like a support vector machine, or SVM, which might specialize in, say, drawing a line to separate all the cat photos from all the dog photos. PCA basically prepares the data, making that separation task way, way easier. So when you boil it all down, the fundamental goal of tools like PCA is really the same. It's about using mathematics to find meaningful patterns and create a little bit of simplicity in what, at first, looks like a hopelessly complex world. And that kind of leaves us with a final thought to chew on. We've just seen how a machine can be taught to filter out all the noise and find the one or two principal components that truly matter. It makes you wonder, right? In the overwhelming data of our own lives, what essential patterns, what core truths might we be overlooking?